Okay, everybody, here we go into section 5.6, and we're kind of moving into the back end of this chapter here in chapter 5. And what your book does with this chapter is they don't really separate integrals from applications of integrals the way they did with derivatives back in chapters 3 and 4. So 5.6 is a section where we're not going to learn how to find any new integrals, but we're going to talk about something new that we can do with them. And that is this phrase right here of looking at the integral as a measure of the net change of a particular function. Net being interesting, like after everything else is considered. So the way we're going to try to focus most of our efforts here, at least to kind of get a sense for what's happening in 5.6, is to go back to our old buddies PVA functions from 3.4. And if you've forgotten what that stood for, that was a little thing I made up for position, velocity, and acceleration functions. And so everything on this slide right here is just a review of some things that we talked about back in the beginning of chapter 3, really the middle of chapter 3, when we were learning how to take derivatives. So what we did is in section 3.4, we defined s of t as being our position function. And I think it's worth writing out just in case we've forgotten that, because of course position begins with a p and not an s. So once we defined what our position function was, that's what was normally given to you at the beginning of a problem from chapter 3. And then just a little extra definition to recall right here that delta S, or the change in position of an object over time, was otherwise known as displacement. And we would measure that by the position at a time B, which was its ending position, minus its position at time A. So an object's ending position minus its starting position was going to get you its displacement, its net change in position. Now, the big takeaway from section 3.4 came right here, that if we took the derivative of our position function taken with respect to time, or that's how it would be written in Leibniz's notation, in Newton's notation we would call that s prime of t, that the derivative of our position function, however way we wrote it, was equal to our velocity function. All right, that change in position over time was the formula for average velocity, but if we made that a derivative, that became instantaneous velocity. And then from there, one more thing that we threw in at the end of that is kind of the same concept, just taken down a level. If we now were to take the derivative of velocity with respect to time, or v prime of t, that's how we came up with our acceleration function. So this was all meant just to remind you guys about something that we learned in chapter 3 that you may have since forgotten, that the derivative of position is equal to velocity, and that the derivative of velocity is equal to acceleration. And with all that in mind, let's get ready to move on right now into where we're going now in this section. So what we're going to do right now is we are going to talk about the fundamental theorem of Calc Part 1, which we discussed back in 5.4, but now we're going to relate it to a PVA problem specifically. So this line right here, you really shouldn't need to write down, although it's certainly not a bad idea, but it's already in your notes, that we can evaluate a definite integral from a to b of our function f of x taken with respect to x by anti-differentiating the integrand. And the way we express the antiderivative of little f of x is capital F of x. But then we evaluate that at its upper limit, then its lower limit, and subtract the results. So this is me leaving out the middle part of this, everybody, which was capital F of x with the bar underneath it, or after it, I should say, and then going right to this, capital F of b minus capital F of a. So that is the fundamental theorem of Calc Part 1. But one of the things they love to check for on the AP test is to see if you guys understand that relationship about how a definite integral works in a context outside of a normal little f and capital F. They want to see if you can do it in other settings. So let's take a look at what's going on right here. If we were asked to evaluate a definite integral from a to b, not of f of x, but of v of t, of a velocity function taken with respect to t, well, let's go back up a level. And we learned that we can evaluate a definite integral of a function by anti-differentiating that function, getting capital F of b minus capital F of a. Well, that same concept is going to work right here, but let's think now instead of just putting a capital V. What function represents an antiderivative of velocity? Well, to answer that, let's go right back to where we were right here when we learned right there, guys, that velocity is defined as the derivative of position. That means if we read that backwards, position is an antiderivative of velocity. So when we go to finish this line now and we try to ask ourselves, what is an antiderivative of our velocity function? That is going to be your position function, evaluated at your upper limit, b, minus at your lower limit, which is a. And you might recognize right there, guys, that what we just came up with, this formula, S of B minus S of A, we wrote down again right over here, that's the formula for displacement. So, as fun as it was for me to put that asterisk right there, let me get rid of that, and let's make sure we write this down. What we just found, everybody, is a formula. Oh, that is not what I wanted to do. There we go. Is a formula for the displacement of an object on an interval of time from A to B. The displacement of an object is found by taking the definite integral of its velocity function from B to A. And I suppose technically it would have made more sense if I put the equals delta S at the end of that, but I think this is what you guys are going to be looking for when you're doing your homework, because there might be a question, in fact we'll see one here in just a few moments, that says find the displacement of an object. And now you've got it, there's the displacement formula. Now, right underneath it, everybody, is almost the exact same expression again. A definite integral now from A to B of the absolute value of velocity with respect to time. And there's not much for me to do here, guys, other than to flat out tell you what it is that we're finding here. This is the formula, everybody, for what we call TDT, or otherwise known as, might want to write this one down, everybody, that is the total distance traveled by an object during a particular interval of time. And we will get into that in just a moment, the difference between displacement and total distance traveled. Actually, I lied. We're going to get into that right now, because now that I think about it, I'm not really sure there's a great example of this coming up. So let's say for just a moment, everybody, that an object is moving along a number line. All right, so let's just draw that out real quick. And nice and simple, we'll just put 0 in the middle of our number line. And let's just say, for the sake of argument, that the object starts right here at 0, and the object moves all the way down here to the right, okay, to a position of 10, and then all of a sudden it journeys all the way back and ends up right back where it started. Pretty simple, right? Okay, two questions then, everybody. What is the displacement of our object, and what is the total distance traveled of our object? And whether or not you already know the answers to these two questions, because you might, is just a question of how well you understand these concepts of displacement and total distance traveled. So the definition of displacement, everybody, is net change in position. It was defined as position at time B, the ending position, minus the position at time A, the starting position. Well, if this object moved to the right and then moved back to the left, its position, according to the number line here, at the end of its journey is at 0, minus the position at the beginning of its journey, which is 0 as well. This object has a displacement of 0 feet or meters or miles or whatever it is that we're talking about right here. The net change of where this object ended up compared to where it started is 0. And yet, everybody, total distance traveled asks something similar but different. Total distance traveled ignores the fact that some of our displacement here was negative, because that was simply the, what did we have here, guys? It was the integral from A to B of just the absolute value of V of t, and then a dt at the end right there. So if we broke this up, really the first interval from 0 to this spot over here, the object moved a grand total of 10 units. Then on the way back, technically its displacement from here back to here was negative 10, but because of the absolute value, we ignore the negative and we simply add a 10 to that, and we found that this object had a total distance traveled of 20 units. Which makes some sense, I think. 10 units down to the right, and then 10 units to get back where it started. So the displacement was 0 because there was no change between its starting position and its ending position, but its total distance traveled was 20 because it moved 10 units in one direction and 10 in the other. So that's a fairly quick explanation there of the difference between displacement and total distance traveled. And then there's one more little thing we're going to throw down at the end right here, and there's not really a name for this one, but if you take the same concept that we talked about above here and apply it now to having acceleration, let me go back to purple here, guys, to having acceleration as your integrand, let's think about what we did here. V of t, and we tried to come up with an antiderivative of velocity, and we got position. Now we're trying to anti-differentiate acceleration. That's going to get us velocity. So this is going to be v of b minus v of a, your ending velocity minus your beginning velocity. And there's no cool word for that, guys, for what it is that we just found. Essentially, that is delta v, the change in velocity of your object during this time interval from A to B. All right, guys, so those are kind of the big ideas of this section right here. Everything up above we have already talked about in a previous section. That's all from 5.4, and now it's these same concepts just applied to a PVA setting, so this is some quote-unquote new stuff here within 5.6. So, as we get into it now, you are going to see, everybody, a whole bunch of word problems, or at least something similar to a word problem, because that's the type of thing we end up solving with this information we have here in 5.6. So, sorry, you're missing the top of that slide. Here we go. This is a problem that we would have covered back in Chapter 3. In fact, if I'm not mistaken, I think when I wrote this problem right here in the notes, I actually did go back to our notes from Section 3.4 and pull this exact problem. In Chapter 3, they would have given you the position function. That's not what I wanted to have happen. They would have given us the position function, and we would have been asked to find displacement. So to do that, back in the day, we would have said, all right, displacement is simply equal to the change in position. So that would be S of, let's see, we're ending this thing at t equals 8, minus its starting position, which is S of 1. And let's see what we've got right here, guys. And of course, I don't have a calculator set up and ready to go, so hang out with me for just a second here, guys. Let's open up our Inspire, and it's overkill for what we're doing right here, but I think we'll be okay. All right, so where were we, guys? We were at, let's see, S of 8, which is going to be 96t minus 16t squared. So let's write that out. So that's going to be 96. Actually, if I was smart, this is what I would do. I'd go ahead and I'd write the expression out, 96t, and then a minus 16, and then a t squared. And then we would look for the evaluation bar, which, shoot, I'm not sure I know where that is on my calculator here. I know where it is on yours, everybody. Let's see. Any chance that would be... Oh, it's under less than, greater than. No, it's not here either. Okay, that might have been a dumb way to do it. So let's do something else then, guys. All right, sorry. We are going to define, and we'll call this thing f of t. All right. To equal, let me go back here, equals 96t minus 16t squared. Okay, that's one way to do it. And then we will do f, here we go, of 8. And I guess that's not what I wanted. I forgot parentheses. Okay, let's try that again. F of 8 is going to equal, all right, negative 256 is what we got right there. Okay, so that's where this thing begins here, guys, at a negative, or I should say that's actually where it ends, at a position of negative 256, minus, and then S of 1. Why did I call this thing F instead of S? That was dumb. Anyway, F of 1 is going to equal 80. So a negative 256 minus 80, and I don't think I need a calculator for that, is going to get us negative 336. We'll find out in a minute if I'm right about that or not. So what that means is that while this object is in motion or flight or whatever we're talking about, from t equals 1 to t equals 8 seconds, this thing's height or position decreases by 336 units, whatever unit it is we're talking about. So that's what a Chapter 3 problem would have looked like, everybody. They would have given us the position function and asked us to find displacement. Now let's take a look at what's going to be different in Chapter 5. Now, instead of us giving them giving us a position function, now they're giving us a displacement function. But you'll notice I'm asking you the exact same question. Find the displacement of the object from t equals 1 to t equals 8. Well, this is a formula we just wrote down a moment ago, so hopefully we've got it now, everybody. The formula for displacement here, delta S, is equal to the definite integral from a to b of your velocity function, v of t, taken with respect to t. And so, where are we, everybody? Let me slide this up just a little bit. So our displacement then is going to be a definite integral, and again, from 1 to 8, so 1's our lower limit, 8 is our upper limit, and our velocity function now is 96 minus a 32t dt. By the way, let me just say, because we didn't know this before, this is the same function that I'm giving you here, guys, and I don't know if you noticed that. If the position function was given to you right here as 96t minus 16t squared, velocity would need to be the derivative of that position function. And sure enough, the derivative of 96t is 96, and the derivative of a minus 16t squared is a minus 32t. So I'm expecting to get the same answer here that I got right there. But I don't want to assume, because you know what happens then, bad things. So let's see, this looks like a derivative that's not going to be too hard to evaluate. So delta S then will equal, antiderivative of 96 will be a 96t. This looks familiar now. And an antiderivative of negative 32t is going to be a negative 16t squared. Oh, there's that position function. And we're evaluating this now from 1 to 8. Well, boy, this looks really familiar now, because I already know what happens when we're going to plug an 8 into this expression right over here. The 96 times 8 minus the 16 times 8 squared. I hate to assume, but that's going to give us the exact same number that it got right here when we put the 8 into the s function here. We are going to get a negative, not that, we're going to get a negative 256. Come on, there we go. A negative 256 by putting the 8 in there, and then minus an 80, and that's going to get us the exact same result of negative 336. Let's talk for just a moment about units, everybody. Our integrand right here, 96 minus 32t, was measured in feet per second. So I'm going to go ahead and write that in here, feet per second. But now what we need to talk about next is a really important thing, and it seems trivial, and I think you guys are going to blow it off. But if we can understand the concept I'm about to explain right here, this is going to help us through a ton of problems for the next 3 months. If you guys remember way back in the day at the beginning of Chapter 5 when we talked about what an integral really was, I told you guys that this dt was representing the width of a rectangle. The integrand was representing the height of that rectangle, and that even though we don't usually talk about it, you're actually multiplying here your integrand by your variable of integration. This was height of a rectangle times the width of a rectangle, and that gave us area of a rectangle. So that means that this 96 minus 32t feet per second is being multiplied by dt. And what is that? dt is very similar to delta t. It means change in time. And the units of time we are dealing with in this problem are seconds. So one thing you guys will hear me say a lot is the connection between this variable of integration and these limits of integration. Time is being measured from 1 to 8 seconds. So what are we really doing here? We're multiplying feet per second times second, and the seconds cancel out. And that is the reason why, not just because we think it should be, that is the reason why this answer is measured in feet. Now, Let me go ahead and just ruin the suspense, although we talked about this a little bit last week, and I think you guys probably know it already. We actually just could have taken this expression right here, and as long as our directions didn't forbid us from doing it, our calculator will evaluate definite integrals for us. So what I could have done, everybody, is gone to my Calc menu. You guys would hit Menu. I got to hit this little wrench here, and then we would do Calculus and Integral. So we were talking about an integral from 1 up to 8, and our integrand was the function, hang on, I forgot it already, 96 minus a 32t. So 96 minus a 32, and we'll put a t here. And you can actually put whatever variable you want there. If you guys would prefer to put an x, that's fine. You just need to make this variable of integration match it. So if you did an x before, you got to do an x now. I did t in both spots, so we'll go with that. And we hit enter, and there is the correct answer. Calculator wouldn't lie to you, of negative 336. Okay, so that's just kind of a summary right here of what it is that we're doing in this problem and how it's, asking the same question but in a different way from something that we did back in chapter 3. Okay, let's see some new stuff with it right here. Whoop, can't see anything right there. There we go, let's try that. All right, guys, so what's happening here? A car is traveling with a velocity given to us by this velocity function here, 35 plus a 2t squared, and that is miles per hour. So they give you the units for velocity, and they also tell you then, right, that t has to be measured in hours. This formula would not work if you were measuring time in minutes. And what's the question now? Find the distance the car travels in 3 hours. Okay, so they're asking us how far the car has actually traveled. So the first thing you guys want to think about here is this a question about displacement, or is it a question about total distance traveled? And the way that I worded it, find the distance that the car travels, it sounds like it's going to be a total distance traveled problem. But if we go back and look at those again, the only difference between this formula right here and this one right here is the absolute value around the velocity integrand. Now ask yourself this question: when does absolute value matter? Absolute value only matters when what you're taking the absolute value of might at times be negative. But if you know that what's inside the absolute value was always going to be positive anyway, the absolute value doesn't really accomplish anything. So if we take a look at this problem, I am pretty sure that we're going to be doing a definite integral of our velocity function, which is 35 plus 2t squared taken with respect to t. And if you ask yourself, is there any value of t that we're going to be looking at here that will make that integrand negative, then maybe the absolute value matters. But as we look at it, guys, t squared is always going to be non-negative, either 0 or positive. Times 2 plus 35, it's always going to be positive. So it really isn't a terrible idea to put the absolute value here, given the way the problem was worded, but it's unnecessary in this case because that integrand is never going to be negative. Okay, what else is going on here then, guys? So our integrand, t is measured in hours, and then we want the distance the car travels here in 3 hours. So without any different directions to steer us in another direction, we're going to say starting at 0 hours and ending at 3. That is not what I wanted. Sorry about that. From 0 to 3. Let's see what we can do with this one here. Now, this one isn't too bad to integrate by hand, so I'm going to do this and maybe regret it, but then I'll show you a little trick on the calculator in a moment. So 35t, and then plus, that's a little ugly, that's going to be a 2/3 t cubed for that antiderivative going from 0 to 3. So what happens here, guys? Let's plug a 3 in there. 35 times 3 is 105 plus, okay, 3 cubed is 27, divided by 3 is 9, times 2 is going to be 18. So that's what we get for f of b. okay, with the 3 minus. And I really don't want you guys to get in the habit of assuming that anytime you're putting in a 0, you're going to get 0 out for your result, but that is what happens in this case. 35 times 0 plus 2/3 times 0 cubed, sure enough, that's going to get you a big fat goose egg right there. So we're pretty well good to go here. And the 105 plus the 18 is going to get us 123. Now, it didn't really say this here, but let's talk about it. 123 what? Let's not make the mistake, everybody, of just assuming what's going on. Let's think about how we got this answer. 35 plus 2t squared right here was measured in miles per hour. So I'll go ahead and write that out as a fraction, miles per hour. We're multiplying that by dt, or delta t, or change in time. And time was measured from 0 to 3 what? Hours. So we're multiplying miles per hour times hours. So sure enough, the hours cancel each other out, and we end up with 123 miles that this thing traveled during its 3 hours there. Okay? And if you do the math on trying to figure out, how fast this thing would be going, then, yeah, I think that seems to make a little bit of sense. Okay, so that was example 2, not too bad. This one gets a little bit interesting here. Glad we're going to talk about this one. A car is traveling at 40 miles per hour when it begins to accelerate at 3t miles per hour per minute. Oh, and now it gets weird here, everybody, because that's a very strange unit. And if I read the problem carefully, that's a unit for acceleration. Now, you guys are used to the units right here of miles per hour, or miles per hour squared when you're talking about acceleration. And miles per hour per minute might not seem like that. But what we really need to remember, guys, is that acceleration is defined as the change in velocity of an object over time. And velocity, okay, well, there's a lot of different units we could use for velocity, but miles per hour is the one we use most often when we're talking about a car. So miles per hour is a unit for velocity. And change in time can be measured in any units of time. Could be seconds, could be hours, days, weeks, months, years, or in this case, minutes. So as weird as it seems, you guys, miles per hour per minute is a velocity unit divided by a time unit. Yeah, that's a valid unit for acceleration. Just a little weird, but you got to think about things a little bit differently as we get into this section. So what's going on, guys? We're trying to find the car's velocity given its acceleration function. So if we go back to this second slide right here, and if I scroll down just a little bit, this is the formula we're going to be using here. Okay, delta v, or the change in velocity, is given to us by the definite integral of its acceleration function. So let's see what we can pick up right here, guys, and what's going on here. We're going to do a definite integral now, and then we're starting the experiment at 0. We're ending it at 5 minutes. The velocity function, which is going to be 3t, is going to go right here, and we're integrating that with respect to t. So let's see where that gets us. Integrating or anti-differentiating the 3t is going to get us a 3/2 t squared evaluated from 0 to 5. Okay, all right, so I always like then to leave the 3/2 alone out in front, and then in brackets, 5 squared, of course, is 25, minus the 0 squared is 0, and that's going to get us, not perfect, 75 over 2, or 37.5. Let's talk units. 3t right here was measured in that goofy unit now of miles per hour per minute. But then we're multiplying that by dt, or delta t, or change in time, which is measured from 0 minutes to 5 minutes. So dt is measured in minutes. And sure enough, miles per hour per minute times minutes, gone, and that leaves us with miles per hour. And at this point, many a Calculus 1 student pats themselves on the back, moves on to the next problem, feeling that everything's right in the world, and then gets a rude awakening a little bit later when they check their answer or they get their quiz or their test back, and they realize, uh-oh, something is amiss. Now, what you may have noticed right there already is that we never used the information that was present in the first sentence at the beginning. A car was already traveling at 40 miles an hour, then it begins to accelerate. And the answer that we came up with, 37.5, is actually less than the velocity it was traveling at to begin with. Now, that is possible, but for your velocity to decrease, the derivative of velocity, or acceleration, would have to be negative, at least for the majority of the time. But this acceleration function, 3t, is always going to be positive anytime t is between 0 and 5. So what gives? Well, I kind of left this out on purpose, guys, because I made what I considered to be a mistake that a lot of you guys just go, yeah, okay, Mr. Fontana, whatever, but it starts to matter at this point. I wrote down a formula without paying attention to what comes, dang it, to what comes out in front of that. So if we go all the way back to the second slide here, come on, there we go. What did we find when we did this work right here? Delta V, the change in velocity for this object over time. So what we've actually found isn't the ending velocity, but rather the change in velocity. So let me go ahead and be thorough now. You should never write a formula without putting something on the left-hand side so you know what it is that you have found. That is delta V. So now let me kind of make up a formula here for you guys. You can do this in a couple of different ways. I like to think about it logically, that velocity at 5 minutes would equal your velocity at the beginning, 0, plus the change in velocity during that interval, in which case v of 0, our initial velocity was 40 miles per hour, and our delta v is what we just found here at 37.5, and that is going to get us 77.5 miles per hour for the velocity of this car at the end of the 5-minute experiment here. Now, if you're wondering where I came up with this little formula, some of you might find that logical. Ending velocity equals starting velocity plus the change in velocity. But if that's a little confusing to you, just try to solve that equation for delta V. And you could do it this way as well, and this shows up on the AP test a lot. To find delta V, that's going to be your ending velocity, which is v of 5, minus your starting velocity, which is v of 0. That's the same formula that we have right here, just solved for the delta V. And in that case, you knew that delta V was 37.5, v of 5 was the unknown, and then the v of 0 would have been 40. And if you add the 40 to the other side, you'd get that same result of 77.5. Okay, I got one more problem that I really wanted to do with you guys, and then I've got one kind of little bonus that we'll talk about in just a second, okay? Let's take a look at what's going on here. So this is a word problem that I think I took out of the previous textbook, so you guys will never see this one again, but what's going on? The United States consumes potatoes at a rate modeled by this function here, C of t, that's a consumption function, as a function of time, I should say, is 2.2 plus 1.1 to the t million bushels per year since the beginning of 1970. Okay, they're being specific about how they lay that formula out, so that's pretty good. Question now, how many potatoes did the U.S. consume in 72 and 73 combined? Okay. Now, let me warn you right off the bat right here that a lot of people want to make this really simple by just plugging a value in for t and just evaluating the 2.2 plus 1.1 to the t power. The issue there is units. If you read carefully, guys, C of t is measured in million bushels per year. C of t is a rate function. So putting a number into that C of t function and evaluating it is going to get you so many million bushels per year. What we are interested in here is how many potatoes. We're looking for an actual number, probably measured in million bushels of potatoes, but not per year. So the question becomes, how do we go from a rate function like C of t, million bushels per year, to just a measurement function, a consumption function here of the number of potatoes? And the answer to that, we are going to have to integrate. We're going to do a definite integral of our consumption function, which is fun to say, 2.2 plus 1.1 to the t power, and we're taking that with respect to t. Now let's think about what that's going to do for us. Again, the integrand right here is being measured in millions of bushels per year. We're now multiplying that by dt, delta time or change in time, and if we measure that in years, the years cancel, and that's going to leave us with how many millions of bushels were consumed during this period. Okay, so we're in good shape. The only question now that we haven't put in here yet, guys, what are the limits of integration? And the key to that, there's actually two tricky things right here. The first key to that is this phrase right here. Whoever came up with this function, probably our friends at the United States Potato Council, maybe in Idaho. Anyway, they said that this function is valid since the beginning of 1970. So January 1st, 1970. We want to know how many potatoes were consumed in 1972 and 73 combined. So we want to begin our measurement of consumption on January 1st, 1972. Now remember, guys, dt has to be measured in years. So the first day of 1972 is how many years after the beginning of 1970? And the answer to that is 2. January 1st, 1972 is 2 years after January 1st, 1970. But now this next one is the second tricky part that people goof up a lot. A lot of people look at this and say, okay, we're going from 72 to 73, so I'll just put a 3 up there. Well, here's the problem. If I do it this way, I start measuring consumption on January 1, 1972, and I end measuring consumption on January 1, 1973. So to do that would not include any of the potatoes that were consumed during the year 1973. We are actually going to the end of 1973. And in kind of the way that water both freezes and ice melts at 32, it's the degrees, it's the same way either way, the end of 1973 is the same moment in time as the beginning of 1974, January 1st, 1974. And now if you notice, there's a gap of 2 between these two limits of integration. That means that we're measuring this consumption over a 2-year period, and that makes some sense. And this one, guys, with anti-differentiating an exponential function with something other than e for the base, I think we're just going to go to the calculator and let it do the hard work for us. So again, I'm going to go to my tools menu. I'm still in calculus. I'm going to do an integral from 2 up to 4, and our consumption function was 2.2 plus a 1.1 caret key, there we go, to the, and again, the variable you use doesn't matter, but I'm going to try to do this right with the t, and we're measuring all this with respect to t. Let me make sure I've got that right. 2.2 plus 1.1 to the t power from 2 to 4. Everything looks kosher to me. So I'm going to hit enter, and there we go. We get a big, ugly, irrational number, and I will remind you guys for the umpteenth time this year that every single decimal that we have to do at this level, we round to 3 places. So that's going to be a 7.066. So let's write that one down before we forget it. A 7.066. That's a bad 0. And again, guys, we were measuring this here in that many million bushels. Which, I don't know, is that a lot? I'm not really sure. Sounds like a lot over a 2-year period. All right, guys. Where we are right now is kind of the end of what we really needed to cover from section 5.6. So if you decided you wanted to stop watching my lovely video right now and just get working on the homework, I wouldn't be that offended. But what I do want to do next is move on to, and this is really the first time this year we've been able to do this, an actual honest-to-goodness AP question. It's a very old one. This was from 2003, and back in those days, oh man, maybe up until like 2010 or 2011, they used to publish two versions of the AP test every year. They don't really do that anymore. So this was Form B, like, so if somebody was sick during the first day, or sometimes just for security purposes, they'd give out Form B instead. So let's take a look at what's going on in this problem right here, you guys. Okay, and by the way, this is about typical length and difficulty here for a free response question on the AP test. You're going to get 6 of these questions and have 90 minutes to complete them. So that's an average of 15 minutes per. So that's about how long it ought to take us to do this. And this type of problem, everybody, you are going to see a lot of here. This is what we are going to classify here as an input-output problem. Both of these things are happening simultaneously. So let's read and see what's going on. A tank contains 125 gallons of heating oil at a time t equals 0. For a reason you're going to see later on right here, I'm going to circle that. That is what we call an initial condition, and I'll come back to that in a little bit later. And of course that occurs at time t equals 0. That won't always be the case, but it usually is. During the time interval from 0 to 12 hours, heating oil is pumped into the tank at a rate according to this function. So this right here, everybody, is our input function. This is the rate at which heating oil is being added to the tank. And of course it's a really ugly function. 2 plus 10 over 1 plus the natural log of t plus 1, but that is measured, this is important everybody, in gallons per hour. And that means that this is a rate function. Okay, kind of like miles per hour or millions of bushels of potato per year. Now, during the same time interval, heating oil is being removed from the tank at a rate given by this R of t function. So that is going to be the output function. That's the rate at which oil is being pumped out. All right, 12 sine of t squared over 47. It again is gallons per hour. So this again is a rate function, kind of like velocity if you want to look at it that way. And what's going on here, guys? Most of the free response questions you'll see on the AP test are 3 or 4 parts. This is an example of one that's 4. So here we go with part A. How many gallons of heating oil are pumped into the tank on the interval from 0 to 12? And let's read that question slowly. How many gallons? Stop right there. So the two functions that we were given, h of t and r of t, are both rate functions. They're both measured in gallons per hour. But this question is asking us how many gallons. So what do we do to go from a rate function, all right, to the accumulation function, from gallons per hour to gallons? We're going to do an integral here, guys, and that's what we've been working on here so far today. We're going to take, and we're talking about gallons pumped into the tank. So we're going to look at our input function right here, h of t, and we are going to do the definite integral, and I'm going to save some time here, guys. I'm just going to write it out as h of t. We're going to integrate the h of t function with respect to t, and we're doing this on the interval from 0 to 12. So 0 is my lower limit, and 12 is my upper limit. And one of the things we're going to have to get used to, and once we know, and it doesn't say it here, but numbers 1 and 2 on your free response test, everybody, are going to be calculator questions. And on a calculator question, that is as much work as you need to show. So what am I going to do? The first thing, and I'll hit this a million times in April and May, we're going to define the functions that we're dealing with. So the first one here is h of t. So I'm going to go to Tools menu and go Actions and then Define, and let's name things the way they are. Unfortunately for me, this is kind of a pain, but okay, we'll make it work. So h of t, okay, let's go back here now, is going to equal, and let's see what that function looked like. It was 2 plus 10 over 1 plus natural log of t plus 1. All right, I'm sure I'm going to screw that up, but here we go. So that equals 2 plus, and then we had a fraction then, so now's probably a good time to hit the stacked fraction button, and I forgot it already. 10 over 1 plus natural log of t plus 1. 10 over 1 plus, oh, natural log here is somewhere. There we go, natural log, and I think this was a t plus 1 if I'm not mistaken, but I'm sure I'm going to have to go back and double check that. I think that was it. So 2 plus 10 over 1 plus natural log of t plus 1. 1 plus natural log of, okay, that should be it. Got it. And now, I guess I can, you know what, while I'm here, let me go ahead and define the other function as well. So we will define, and this one was going to be r, parentheses, where'd you go? There you go, r of t, and that was going to equal, let's go back here, and this one had some trig in there, didn't it? R of t, 12 sine of t squared over 47. Okay, so 12 times the sine of a fraction here, this was going to be t squared all over 47. Okay, we're in pretty good shape right now, so we will hit enter. All right, and now we're in good shape. So what we were trying to do here was to do a definite integral. So I'm going to go to my calculus menu. So for you, I believe this is menu 5.3 for definite integral. Maybe menu 43, that sounds right to me. You guys check. Anyway, it was an integral from 0 to 12. And now, guys, for our integrand, since we've defined the function, let's just go ahead and call this thing what it is, which is h of t. And I don't know that I have an h anywhere I can get to from here. Nope, so I got to go back to the keyboard here. Kind of a pain. But h of t, integrating all that with respect to, no, I do have a t here. Okay, that should be all I need to type in. So when I hit enter, nice and simple, I got 70.571 as we round to the nearest thousandth here. So 70.571. Now, one important thing we'll talk about a lot when we're doing the AP practice stuff, if they don't ask you to include units, don't include units. But we know this is measured in gallons. Why? Because h of t was measured in gallons per hour, and then we multiplied that by dt, the change in time from 0 to 12 hours. So gallons per hour times hour is going to get us gallons. Okay, that was part A. Okay, let's talk about B now. Is the level of heating oil in the tank rising or falling at a time of t equals 6 hours? And we're going to give a reason for your answer. Okay, so at this point, everybody, now what we would need to do is we would need to think about rates. If the input rate is greater than the output rate, that means then that oil is being pumped in a greater number of gallons per hour than it was being pumped out. So if the input rate exceeds the output rate, then the level of heating oil will be rising. But if the input rate is less than the output rate, that means that heating oil is being taken out of the tank faster than it can be replaced. Well, in that case, then, everybody, our level would be falling. So now what we're going to do is we're going to go ahead and we are going to evaluate H at 6, and we're going to evaluate R at 6. And let's see what those rates actually look like. Now, this is going to be really easy for us since it's already defined in the calculator. So for us, guys, we are going to do H of 6, and that's it. Just hit enter. Oh, I didn't want that. All right, so let me get a decimal approximation for this. There we go. So 5.395 is what we get for H of 6. 5.395. And if we care, everybody, that was in gallons per hour. And now how about R of 6? So let's try that one. So that is going to be R of 6. And let's go back here. And again, I think I just want the approximate value there. 8.319 for that one. 8.319 gallons per hour. And there's a lot of different ways to justify your answer or to give a reason, but what I would say, and there's not just one right answer right here, but we could go and answer the question clearly. We would say that the level of heating oil, I get it, is falling at t equals 6, and the reason for that would be because R of 6 is greater than H of 6. Okay. Another way they might have justified it is that with H of 6 being the input rate and R of 6 being the output rate, they might have also justified it by saying then that H of 6 minus R of 6 is negative, which means then that the output rate exceeds the input rate. Both of those are valid ways, and they're both driving at the same conclusion. So I think those will both work. Okay, I'm going to go to this next slide, but it's the exact same problem, guys. I just wanted to give myself room to talk about parts C and D. All right, so let's see what's going on at C here. This is like kind of the important question right here out of all four of them. This is just really getting down to it. How many gallons of oil are in the heating tank at 12 hours? Okay, so what we have to get used to, and I promise you, you will see this many, many times over before the actual AP test, whenever that's going to be. With an input-output problem, they will almost always ask you, what is the overall volume of what you're dealing with? And there are three considerations, okay? Basically, guys, I'm going to write this out. There's the initial volume. That impacts how much you end up with, plus the amount that you put into whatever receptacle it is you're talking about, minus the amount that came out of that receptacle. The initial plus the input minus the output. That's what we need to think about. Okay, so what I would probably do is make up something like V of 12, V being my volume function. And the initial amount that we started with, you guys saw me circle that a while ago, and I said I would talk about why. It's because that initial condition right there is really, really easy for people to forget about and ignore. But it always comes into play on this type of question right here. So 125 gallons, that's our initial amount. Plus, now the input, I think we already answered this, but I'm going to go ahead and just write it out again. I think this is all the work that we actually did here in part A. So even though I know the answer, I want you guys to see the symmetry here. It's going to be plus the integral from 0 to 12 of your input function, h of t dt, and then minus the number of gallons of heating oil we have lost from the tank during that interval, which is going to be very similar. That'll be an integral from 0 to 12, but now of your output function, which is r of t dt. And as messy as that expression is, everybody, it's not going to be that bad to put into my calculator. And I'm actually going to show you a trick here. Since these two integrals use the same limits of integration from 0 to 12 and have the same variable of integration, dt, I can put those together into one integral in my calculator. And let me show you what that's going to look like. So we're going to begin with a 125. We're going to add to it a definite integral here. All right, starting at 0, ending at 12, and the integrand now was going to be our input function, which was h of t. Okay, got it. And actually, I can keep going here from the keyboard, can't I? Minus, and then the output function was going to be r of t. Okay, and we're integrating all of that with respect to t. And that should do it, everybody. So if I want the approximate value right there, this is what we end up with. 122.026 would be our answer here. 122.026. Now, once again, they didn't ask for units, so I'm not going to write them, but they said how many gallons of heating oil are in the tank? Well, 125 was in gallons. This integral was gallons per hour times hours, so that's gallons. And this one here, gallons per hour times hours, is also gallons. So gallons plus gallons minus gallons, yeah, sure enough, that's going to be gallons, even though if they didn't ask for it, we shouldn't put it there. And I think that answer seems realistic. I guess this tells us, everybody, that the overall output in the tank during these 12 hours is just a little bit more than the input, because the value of gallons actually went down from 125 to 122.026. Not much, but some. Okay, now for part D. At what time, T, in that interval from 0 to 12, is the volume of heating oil in the tank the least? So they're asking us to find the lowest value, or the lowest time, for the heating oil's volume right there. Guys, what they're asking us for here is an absolute minimum value of this particular volume function. And it says show the analysis that leads to your conclusion. So now what we need to do is go back to something that we were doing in chapter 4 and talk about where a minimum function or the minimum value of a function can possibly occur. And what I'm hoping you guys remember here is that a minimum can occur either at critical points or at endpoints. So we've got a little bit of work to do right here. Now, actually, what I'm going to do right now is I'm going to kind of figure out and draw a more general case of what I did right here for V of 12. And I'm going to make this a little bit more generic and just say volume at any particular time. Well, it always starts with that initial amount of 125. And we're going to add to that now a definite integral that starts at 0 and ends at whatever time value you want to call it now, guys, of our input function, which was h of t, minus the output function, r of t, measured with respect to t. So that's a really important step right here. That's how you measure volume at any time t. A maximum, or in this case a minimum value, can occur at critical points and endpoints. Well, we know that the endpoints are 0 and 12, but we need critical points. And critical points are anywhere that the derivative of a function is either equal to 0 or undefined. So let's start differentiating this. Well, hopefully we recognize the derivative of 125 is just going to be 0. And the derivative of this function right here, we're taking a derivative with respect to t of a definite integral with a constant on the bottom and t up on the top. Guys, that's fundamental theorem of calc part 2. The derivative and the integral cancel each other out, and I just get h of, and normally there would be a variable change, but that one goes from t to t again. So this is just h of t minus r of t. And if we want to know where that velocity, where that v volume function's derivative is equal to 0, I'll just bring that term to the other side and get h of t is equal to r of t. So the critical points, and I say points, there might be plural, will occur anywhere, you guys, that h of t and r of t are equal to each other on the interval from 0 to 12. So our calculator will do that work for us too. We are going to, no, not that. I'm going to hit my wrench again. I'm going to go back to my algebra menu now, guys. So for you, it's going to be menu 3 and then number 1. We want to solve here. We want to know where, let's get this right now, h of t, close it off, okay, is, lost it here, equal to, here we go, r of t. Now, everybody forgets this, so remember, you got to put a comma at the end of that and then tell it what variable you want it to solve for, which for us is obviously going to be t. Okay, and with that in mind, let me ask for an approximate solution right here. Oh boy, and I got a bunch. So now what we really need to pay attention to, guys, and you'll notice these solutions are in numerical order from least to greatest. The interval on which we're focusing on here is just from 0 to 12. So as I'm looking at this, I don't know how many solutions there are, but I can tell there's only 2 in my interval, the second and the third. So 4.790, let's write that one down. So t equals 4.790, or another one here at t equals, and that one was 11.318. All right, 11.318. So what we found here, everybody, are 2 critical points, and we also need to consider the volume in the tank at the endpoints as well. So we are going to have to measure 4 different volumes here. V of 0, V at our first critical point of 4.790, at our second critical point, volume at 11.318, and also volume at the end of this experiment, which is going to be 12. Well, lucky for us, we already know 2 of these answers. V of 0 was the amount of oil in the tank at the beginning of this experiment, which was 125 gallons. And V of 12, I think we answered right here, 122.026. Gotcha. Now, it's going to be more work to evaluate the volume at the two critical points, but hopefully not too bad. We're going to go to our calculator and basically put in this function here, or better yet, this whole expression. So I'm going to just start. I'm only doing it twice, so that's not too bad. So I'm going to type in a 125 plus, we're doing a definite integral now, so I'm going to go to my calculus menu and integral, and we are going from 0 to, and our first value, I can see it right above me here, is 4 point. Now what we wrote down on our paper was 790. But guys, it's always a good idea to take a moment and type in, you don't have to do all of them, but a few extra decimal places just to make sure that we've got everything right here. And the integrand, oh, I'm getting tired of writing this here, was going to be h of t minus r of t. All right, so here we go. H of t, close it off, got it, minus r of t. All right, close all that off, and we're integrating with respect to t yet again. Okay, now because I typed in a decimal, I think it's going to automatically give me a decimal here. Okay, and I got another answer that's in the ballpark right here, 149.408. So 149.408. Now clearly that's not a minimum, but I still want to write this answer down to show the people that are going to be grading this that I knew what I was doing. My hunch would be, you guys, that this is actually the maximum value, and I have a feeling then that this one right here that I'm about to find might be the minimum that we're looking for. Now, I can save a little bit of time and effort. I can just hit up, and then hit enter. That copies and pastes the last equation, and everything is the same except for that upper limit of integration, that instead of 4.79 blah 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 is going to be 11.318, and let's type in a few more places, 470, there we go, and we'll hit enter there. Okay, 120.738, oops, 120.738. Okay, so what have we found, guys? If we take a look at these four spots right here and we look at the volumes, okay, let's remember something we did from back in the beginning of chapter 4. 125 right here ends up being what we call a relative minimum. It's a minimum because right after that, it goes up to a higher amount. This is a maximum. And since that's the biggest number of all four, this is actually your absolute maximum. What's next? That 120 that we came up with is the lowest value out of all four, so that's the absolute minimum. And then it goes back up slightly to 122. That's what we call a relative max. And I want to remind you guys that unless a function is not continuous, your minima and maxima always alternate. Min, max, min, max. Now, let's make sure we're answering this question correctly. Question D is asking us, at what time is the volume of heating oil in the tank the least? So they're not asking what is that minimum volume, they're asking you at what time. So we would have to answer the question here thoroughly. Oh man, this is a pain, sorry. And we would have to say something like, okay, something like the volume, blah, 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 reaches a minimum at, and they wanted to know at what time, so that's right here, the absolute minimum, at t equals 11.318 hours. And that, finally, everybody, is the answer to that question. Volume reaches a minimum at t equals 11.318. Hey, guys. That's our first free response AP question that we've done from start to finish. Probably took me longer than 15 minutes, but trying to explain some things. Hopefully 5-6 makes a little bit of sense. You guys enjoy the homework there, and let me know when you have questions.